Today, we are going to be looking at a cylindrical system. We're going to be looking at heat transfer. So this will be Fourier's law. And we will look at cylindrical systems. So this is going to be 1D. It'll be 1D in the radial direction. So I'm going to draw a segment of a pipe here. We'll have some sort of pipe. And I think what we'll do is choose something like steam. So it has a nice constant temperature inside. And this hot steam will be cooled by convection on the outside. So we'll have some cool air at T infinity is a common way that we'll write air temperatures if it's convective cooling. TF is also a good choice. Although TS might not have been a good choice here because often we use S as the surface that's being cooled by the air. So we can do this, but that's fine. We'll have a heat transfer coefficient. Remember, we looked at convective cooling. We derived both the mass transfer coefficient and the heat transfer coefficient. One was K sub C, and the other was H. So H was that term that was in front of the temperature difference, the delta T, that kind of controlled the rate of cooling. So we can call this T naught, I guess, at the outer wall. And that would be something interesting to find. We don't necessarily know what that temperature is. But what we want to find here is what is the profile, what is the temperature profile as we move from the inner radius in this pipe outward towards the outer radius. So that's what we want to find out. What is TRI going to TRO? And like I said, we have one-dimensional transport. It'll be radially outward from the center of this steam pipe. All right, so what we need to do then is set up a control volume. We can set up an annular control volume. I'm going to let this be thin in the direction of transport. I'm going to let it go all the way around this pipe. And this is going to have some thickness of delta R. So this control volume that we're setting up is what we call an annular control volume. And if we're going to draw this control volume, actually it'll be interesting for us to, let's choose a control volume that does go all the way around, but we'll also let it be thin or small in Z. So in this cylindrical coordinate system, we'll have R, into the page will be Z, and then if we swing R around, we'll be able to measure a theta. So that kind of looks a little odd, but Z is into the page, R is any radial direction, and if we think about changing R, we're changing theta. So let's look at this small control volume. It's going to have delta Z length, a delta R wall thickness, and it'll go around in 2 pi. So it goes around 2 pi r, it has a delta R thickness and a delta Z length. Has anyone taken multivariable, I think is where you would get this, and know what the volume of a differentially small but finite control volume would be? I think it would be 2 pi r delta z. And I think it'll be worthwhile taking a bit to derive this. All right, so let's take a look at this and why this would be true.